So, overall, test 3, pretty good, right? It's pretty good. So, chapter 3, excuse me, thank you, was the median score was like mid-high 80s, so it's good.
I still haven't taken it.
Well, it's a median, so it's less outlier.
Oh, okay.
Like it's less outlier dependent.
All right, I got you.
I typically stay away from the means because if there's anybody with like a missing or anything, it just craters the mean.
Maybe we should use it.
Thanks, Luke. Peyton, for you. But overall, pretty good. Once everybody's had a chance to take the thing, we'll talk about it a little bit more. And if you're itching to see something, you can always come talk to me during community time. I'll be happy to let you look at things beforehand without passing them back. But overall, pretty good. Pretty good. Today, we're going to finish up section 3.6 and do section 3.7. 3.7 and 3.8 are both like application-y sections, so there's not a lot of technique involved. It's just going to be like, here's a real-world context in which you could use calculus to do this, blah, 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 blah. So in a way, it's going to feel a lot like, some of the problems are going to feel almost like 2-1 problems, where you're going to be like, potentially even finding a secant line or something, and using that to approximate a value. But we'll get there. Okay. So we'd started 3.6 previously, right? We decided to break at 3.5 for the test, with the exception of the derivative rules for logarithms that I said that you guys were still responsible for. So just to refresh our memory, the derivative of a logarithm is just going to be 1 over x times the natural log of the base of the logarithm. So in the case of the natural log, that just turns into 1 over x times the natural log of e, but what's the natural log of e? 1, so it just 1 over x, right? You would have seen that for the test, right? Yeah. So let's do a couple of examples where we have just some derivatives that involve logarithms, and we'll talk a little bit about logarithmic differentiation, and then we'll be out of here, out of this section. So again, all we're doing here is differentiating. If I look at this guy here, what do we notice? To do this derivative, what are we going to need to use? Chain rule, right? We see one function inside of another. Excellent. So the outer is the natural log, which the derivative of the natural log is 1 over x, but we have to plug the inside back in. So it's 1 over the inside. And then we have times the derivative of the inside, which is 3x squared. So we're just going to write that as 3x squared over x cubed plus 1. right? No big deal. Okay, what if we have y equals the natural log of sine x? What do you notice? It's another chain rule problem, right? What's the outside? The natural log. So the derivative of the natural log is 1 over x, but in this case, since it's a chain rule, it's really 1 over the insides. And the derivative of the inside is cosine. So we could multiply those two guys together to get cosine x over sine x, which is the same as cotangent. Very good. That would be our best answer. What do we notice here? It's another chain rule, but what's the outer this time? The square root function, right? Now, when we're going to think about this, probably makes more sense to think about it this way, right? So if I do the derivative of the outside, that is going to be good. And then the derivative of the inside? 1 over x. So if we put this all together, we could write it that way.
Why is the ln x on the bottom?
The exponent is negative. Right? Negative exponent makes a reciprocal. So that's
Right.
1 over the square root of ln x.
And it's negative because you did the little put it down.
Yes, the power rule. Yep, the little put it down thing. Okay. Okay. Let's do this as just log, though, instead of ln. We haven't done a log one yet. Okay, what do you see here? Okay, there's a quotient rule with a chain rule and another chain rule. What if I told you when I see this, I see 3 unlinked chain rules?
Oh yeah.
Yeah, so what we're going to use, what I would recommend using in this point are my properties of logarithms. So if you remember way back to Algebra 2, when we talked about expanding and condensing logarithms, we had these 3 properties. Of logarithms that we use to expand and condense things. This is going to take something that could be a pretty complicated derivative to take and turn it into 3 pretty easy chain rules, which is what our preference would probably be. So remember, for expanding, the typical order we go, unless there's like a parenthesis indicating some other kind of order of operations, is quotient, product, power. So here, I would start by using the quotient property. And at the same time, I'm going to think about the square root as just the 1/2 power. No products going on here, right? No product property. I'll use the power property then to move the 1/2 as a coefficient. No calculus has been done yet. I just want to point out to you. I haven't done any calculus yet. I'm just using my properties of logarithms way back from Algebra 2. But why is this effective? It got rid of one of the chain rules, right, with the square root, and it gets rid of the quotient rule. Particularly the quotient rule is the nice one to get rid of, right, because that's a pretty big hassle. These two derivatives that I'm left with now are pretty easy, right? If I take the derivative of log of x plus 1, well, the derivative of a logarithm is 1 over x, or 1 over the inside, times the natural log of the base of the logarithm. When it's just log, we recognize that as log base 10. And then we have times the derivative of the inside, which is just 1. And we'll do the same thing here. And then times the derivative of the inside, which is just 1. So I would not bother finding a common denominator or anything. That feels, oops, that's not supposed to be log, that's supposed to be ln. That feels like more trouble than it's worth to me, because definitely nothing's going to simplify nicely with those natural logs down there. So I would just probably leave it there. Does that feel okay to you guys? Here's a question. What if I want to do the derivative of the natural log of the absolute value of x? Well, here's the trick, right? So we're going to go back in time to like Algebra 1 and look at the definition of an absolute value. So the absolute value is just x when x is greater than or equal to 0. And it's equal to negative x when x is negative. Right? So if I take the absolute value of -4, I plug in negative of -4, and it gives me a positive back. Right? This is the piecewise definition for an absolute value. So if we go and take the derivative now, what's the derivative of the natural log? 1 over x. And then what's the derivative of the natural log of negative x? That's a chain rule problem, right? So it'll be 1 over negative x times the derivative of negative x, which is negative 1. And what do you notice? It's just equal to 1 over x. It's kind of a surprising result. Oh, Mr. Kulik, you dum-dum. These should be strict greater thans. Why? Can I take the natural log of 0? Nope! That was the problem. Natural log of 0 is undefined, so I just wrote down the definition for the absolute value of x, not thinking. It's like, oh yeah, it's the natural log of the absolute value. Okay, so that's just like a random aside, but that, again, I think that the AP test kind of likes throwing the absolute value things in there, here and there. So just be cautious of that. And then we touched on this. Oops. Before the chapter 3 test, and I saw some of us trying to use this to varying degrees of success. So this is a technique that can allow you to potentially make the calculus easier on a derivative problem. The catch is it typically is going to make the cleanup, the algebra cleanup at the end, more difficult. So it's like it's a trade-off. Would you rather have difficult calculus and maybe easier algebra, or easier calculus but more difficult algebra? So let's look at a couple of examples here. So if I look at this problem, this looks like kind of a nightmare, right? If I'm going to take the derivative of this, right? I see a product rule, I see two chains, I see a quotient, I see a lot of time. Everybody agree? So in a case like this, where the chains that I have are really just power rule chains, right? Like one of the chain rules is to x to the 5th, the other is x to the 1/2. They're both just power rules. These are nice candidates for logarithmic differentiation. If instead of like the square root of x squared plus 1 on top, I had like cosine of x plus or x squared plus 1, much less appealing to me to want to do logarithmic differentiation. Okay, the first step is to just take the natural log of both sides. On the left side now, I can use my power properties of logarithms to take this from a complicated derivative problem into several simpler derivative problems. So I begin by doing the quotient property. That's the first thing we check for. We do indeed have a quotient. So I'll rewrite that as the log of the numerator minus log of the denominator. If I look at that first logarithm then, I see a product, so I can use the product property for logarithms to write log of the first factor plus log of the second factor. And then I can use the power properties, or power property, to move those exponents to the coefficient outside the logarithms. So far, so good. Now I'm ready to do the calculus. So when I do that, I'm going to take the derivative of both sides. What's the derivative of the natural log of y? What's the derivative of the natural log of y with respect to x? 1 over y, and then because I'm differentiating a variable that's not x, I also get a dy dx. Very good. And then to take the derivative of 3/4 natural log of x, well, that's easy. That's just 3/4 times 1 over x. The derivative of the natural log of x squared plus 1 is a chain rule. The outer function is the natural log. So I have 1 over the inside times the derivative of the inner function, which is 2x. And if I go to the last logarithm, minus 5 times the natural log of 3x plus 2, again, a chain rule. So I'm going to have 5 times the derivative of the outside, which is 1 over x, but I have to plug the inside back into that, so 3x, or 1 over 3x plus 2. And then times the derivative of the inside, which is just going to be 3. So if I take the right-hand side, we can simplify this a little bit. But we want to get the derivative. We want dy dx. So what do we still need to do? I need to multiply both sides by y to get the derivative by itself. Now, am I going to write it as y? No way, Jose, because I know what y is in terms of x's. It's the original. And then you have a whole lot of not so fun algebra to do, potentially, if you chose to go that route. What would we need to do algebraically? We need to make a common denominator in there, add the numerators together, then distribute through that coefficient or that factor out front. It makes a bit of a mess We're not going to do it. This is okay for me. What's the difficulty in particular on a Mr. Kulik style test if you're using logarithmic differentiation on certain problems? If it's a show problem where your answer at the end has to be a certain format, this route could be really difficult, right? Could be really difficult going that route. Not impossible, let me be clear, and maybe not even that bad, but it potentially could be very messy. Not wrong, though. Everybody's cool? Let's do another example. What do we want to do with this? Where you have an x as the base and an x as the exponent. Is this exponential? No, not really, because the variable is in the base. Is it polynomial? No, not really, because there's a variable in the exponent. This is like some weird thing where it's like none of my rules for doing derivatives really apply here, right? Everybody agree? So what can we do here? This is a kind of a problem that screams, please use logarithmic differentiation on me, where I have a variable in the base and a variable in my exponent. I can then use the product or the power property and now when we're ready to differentiate, now I have two factors that are easily differentiable, right? Square root of x and natural log of x are both things I can handle pretty easily. So we'll take the derivative of both sides. When I take the derivative of the natural log of y, what do I get? 1 over y, and then dy dx. When I do the derivative of the right side, that's a product property. So the derivative of the square root of x is 1/2 x to the negative 1/2, and then times the natural log of x, plus square root of x times the natural log of the derivative of the natural log of x, which is 1 over x. So far, so good? Okay.
If the ln x was anything other than ln x, would you have to use the chain rule there?
If there was something other than an x inside of it, yes. Yeah, but since it's just ln x, not ln x plus 1 or something, we don't need a chain rule. Okay? So what do we have here? We have the natural log of x over 2 square roots of x. And then how do I simplify square root of x over x? this is the way that Mr. Kulik would think about it. I would think about x as the square root of x squared. So I can do that. And boy, howdy, almost to a common denominator now. That's going to be much nicer than any reducing I might potentially have to do later, right? Are we okay? It's okay. There's a sneaky reducing trick Mr. Kulik pulled. It would be fine if you didn't notice that, right? You still just go making your common denominator, right? S squared x over x, and you make your common denominators. It'll eventually simplify down to the same thing I'm about to get. Just might take a little bit more work. So make a common denominator. And then my last step will just be to multiply both sides by y. And we'll call that a day. Mackenzie. This part? Okay, so I just thought of x as the square root of x squared. So that I can reduce when I multiplied. So square root of x over square root of x squared is just 1 over square root of x.
Okay.
Right? I just made the simplifying a little bit easier and made the common denominator going to be a little bit easier to find on the next step. Now, if you didn't notice that, is it the end of the world? No, it'll be fine. Making your common denominator is going to be a little bit worse. You know, like to factor and reduce afterwards will be a little bit worse, but it won't be devastatingly bad. It's certainly well within your capabilities of dealing with. 100%. I have high faith that you would know what to do with that. You just have to slow down and go back to Algebra 2, where we dealt with like rational functions and adding and subtracting rational functions. But this isn't even a difficult one to deal with because it's, you know, they're all monomials, so just you make your common denominator is really easy. There's no factoring that needs to happen. That's it for 3.6. It's really just introducing the derivative rules for logarithms and this technique of logarithmic differentiation. And to remind us that we have these properties of logs that we can use. So the homework sets there are all just like derivatives with logs in it for the first block, and the second block is logarithmic differentiation practice. Okay, let's start and see how far we get in 3.7 here. So 3.7 has no like big conceptual ideas. Rather, it's just like taking these ideas that we've been building on and applying them to natural and social science settings. So, for example, we have the position of a particle given by the equation S is equal to f of t, which is t cubed minus 6t squared plus 9t, where t is measured in seconds and s in meters. Find the velocity at time t. Well, what does this problem scream of? It's like a chapter 2 problem, right? What's the relationship between position and velocity? Velocity is the first derivative of position. So what do I really just need to do here? There we go. Done. Really easy, just power rule derivative, right? Part B asks, what is the velocity after 2 seconds and after 4 seconds? What would I be doing there? Well, I'm just going to be plugging 2 in for t, since t is representing time, and plugging 4 in for t, since 4 is representing time. So what do we got here? 4 times 12 minus 24 is minus 12 plus minus 3 meters per second. We got 16 times 3, that's 48. Minus 48 plus 9 is 9. Part C says, when is the particle at rest? What does at rest mean? Not moving. That would be when the velocity then is 0. So, okay. So we just need to solve the equation. 3t squared minus 12t plus 9 is equal to 0. To solve a quadratic, what are the different methods we have to solve a quadratic? Factoring is, I think, the F word you're thinking of. Or the quadratic formula, right? Those are the 2 primary methods that we would use here. I would notice here right from the get-go that every coefficient is divisible by 3. So if I divide both sides by 3, I could get this, and that looks very, very factorable to me. If I didn't notice that, could I just use the quadratic formula right from jump? Sure. Yeah, absolutely you could have. No problem. So what multiplies to give us positive 3 and adds to give us negative 4? Negative 3 and negative 1. So there's our solutions at 3 seconds and at 1 second. The particle's at rest. Says, when is the particle moving forward? What does that mean? What would forward mean? Notice in parentheses it says that is in the positive direction. Means with the velocity has to be positive. So what are we solving? That piece, right? Okay. Well, I'm going to use my result from before. So I have 2 things multiplied together need to be positive. When does that occur? When both are negative or when both are positive. So I would need that situation or this situation. So when t is greater than 3 and t is greater than 1, what is that really the same as? Oh my goodness, Mr. Kulik, that was wrong. Ignore that for a moment. All right. When t is greater than 3 and t is greater than 1, what's that really the same as? Just greater than 3, right? And this one says t is less than 1 and less than 3. What's really that the same as? Just less than 1, right? So this thing is moving positive then from negative infinity to 1 or from 3 to positive infinity. Well, I shouldn't really say negative infinity there, right? What should I really say? Because t is time. So 0, yeah.
Why did you put the negative all those?
So if we were to like sketch a picture of this, where this is like my time axis. Oh, no, let's make this like a position or something. So at t equals 0, maybe are we getting ahead of ourselves?
Yeah.
Probably. Oh yeah, we're doing part E. So draw a diagram to represent the motion of the particle. Okay. So here's what I'm going to do. So we know that there's 3 times that we care about, right? What are the times we care about? We care about t equals 0, t equals 1, and t equals 3. Because that's where we know the particle is changing from moving forward to backwards, right? So if I go back and plug in those times into my original, I can figure out the position of the particle at those times. So when I plug 0 in, I get a big fat 0 there. When I plug 1 in, I get a, what do I get? Negative 2. I meant positive 2, definitely. And sorry, not 2, but 4.
So you have the plus sign.
I'm plugging them into the position function.
Oh.
This one up here, not the velocity function, right? S is the positions. And if I plug 3 in, I have 27 minus 54 plus 27, which is 0. Okay, so what's going on here? Here's my particle starting at time 0. We go forward or something until we get to time 1 where we're at position 4. And then we backtrack, start moving backwards to time 3, where again we're back at position 0. And then from there we move forward in perpetuity. So that's kind of what the particle is doing. Is everybody okay with the picture I drew there? That motion diagram? Again, all I worried about was the places where it was changing direction from going from forward to backwards, and then found the positions to go with it so that things were scaled appropriately. Right, like we have I don't know, like 1, 2, 3, 4 tick marks or whatever. We're gone 4 tick marks over. All right. Everybody's okay? Let's see what F says. There's a million parts to this, right? Find the total distance traveled by the particle during the first 5 seconds. This is going to be a little tricky, right? Because if I just look at the position at t equals 0 to t equals 5, it's just going to show me that much has happened. Right? It's just going to do, I'm going to get that much distance traveled. So what I'm going to need are the forward parts and then the backwards parts. So forward, we're going from time 0 to time 1. Backwards, we're going from time 1 to time 3. And then forward again, we're going from time 3 to time 5. Everybody's okay with that? Well, that's really nice because I know how far I went from time 0 to time 1. How far did I go? 4 units, right? And I know that's also really nice because going from time 1 to time 3 is really easy. How far did I go there? 4 units, right? It's got to be the same distance traveled. Everybody agree? So that's 4. So all I really need to do is figure out how far I went from time 3 to time 5. Everybody agree with that? So that distance is going to just be s of 5 minus s of 3. And I already know that s of 3 is 0. So I'm just going to plug in 5 to my position function up here. So 125 minus 150 plus 45 is 20. You could use your calculator. So my total then is 4 plus 4 plus 20. And I think the units were in meters, right? Well, it's a different schedule. I have it written down up here. 9 is when the class ends. No. Does not appear to be.
Oh, wait. What is this? You do first, second, and then the add.
5, 6, and then there's 2 adorations. So depending, you'll either go to prayer first, lunch, and then class, or class first, lunch, and then prayer, depending on whether you usually have lunch 1 or lunch 2.
So it's dependent on your 3rd hour?
Your 7th hour, yeah, whatever your usual lunch schedule is. Yeah, and then if you had 3rd lunch, there's some people that are going to lunch 1 and some that are going to lunch 2, depending on who your teacher was.
So you go through those teachers.
Lunch 1, Oseki, Pakula, Palega, Schneider, Zimmerman.
Okay.
Lunch 2, Garcia, Hall, Kroll, McGinnis, Moody.
So lunch 1 would be lunch, then prayer, then last hour, right?
Prayer lunch class.
That's lunch 1.
Mm-hmm. Lunch 2 is class lunch prayer.
You
Prayer lunch class. It's lunch.
Oh, so that's the same thing as lunch prayer.
Yeah.
Ah, okay.
So then do we go 7th hour before going?
I don't know that yet. I assume that they'll make an announcement later on to remind everybody what to do. I don't honestly know that. I'd have to go back and search some emails to figure it out. But that's a 7th hour problem for me rather than a 5th hour problem. All right.
I need to learn.
And then part G says to find the acceleration at time t after 4 seconds. What is acceleration? It's the second derivative of position, or really the first derivative of velocity. Either way of thinking about it is fine. So when I take the first derivative of velocity, I get 6t minus 12. And this was asking us for the acceleration at time 4. Oops, I don't know why I wrote stupid Mr. Kulik. So that's 12 meters per second squared. Okay. There are 2 more parts to this question that I forgot to screenshot in here, like a dum-dum. You want to do them?
2 more parts.
Yeah. It says to graph. It said to graph the 3 position, velocity, and acceleration functions on the same axis with the interval from 0 to 5. So let's do that. Well, it's position, velocity, and acceleration. We're going to graph all 3 of them. Okay, we wanted to graph this from 0 to 5. And I don't know, negative 10 to 10 probably isn't sufficient, right? Because we already saw that the at 4, the acceleration is going to be bigger than 10. So maybe I'll make that like 20 or something. So this is the position. Here's velocity. And there's acceleration. Everybody okay with that? On your color calculator, that'll come out a little nicer because you can color code them, right? And then the last part, that would be, yeah, or sketch or whatever. But as far as I'm concerned, that's like a just look at it on your calculator kind of problem. Part I says then, when is the particle speeding up and when is it slowing down? So what is that asking about? Speeding up and slowing down. That's the acceleration, right? Speeding up means that your acceleration should be positive, and it's slowing down, the acceleration should be negative. Ooh. Hold on. That's not quite right. What else needs to be true here? Yeah, velocities has to be positive also, right? Because you could be slowing down faster if your velocity is negative. So now you're slowing down faster or whatever, right?
Couldn't we just look at the graph?
Yes! You could also look at the graph, but I want to talk about like what we're looking for also, right? Before we start looking just at the picture.
No, I just
No.
So I was going to put my
So let's take so those are the 4 scenarios. So I've gone ahead and turned off the position function, just looking at the acceleration. So if I take a look at this, the only place where velocity is positive and the acceleration is positive happens right here at, what is this, t? Or starts happening at t equals 3, right? We already solved for that. So this is after time 3, we're speeding up for sure. If I look at the graph, where are we both acceleration and velocity negative? Starting from this time, which is 1, because that was the other place where velocity was 0, to this time, which is, we're not sure, right? But what time is it really? When is acceleration 0? At time 2, right? If I just solve this acceleration equal to 0, we get 2. So from 1 to 2 is the other time we're speeding up. Is that okay? So where are we slowing down? Everywhere else. So where the acceleration is negative but the velocity is positive, that was from 0 to 1. And the place where acceleration is positive but velocity is negative was this spot from 2 to 3. Ooh. That was a lot of stuff, right?
It was a very long problem.
Well, it had H parts, or I parts, I should say. So, all right. Let's go and look at my next example. This is science-y. Yeah. So this says, if a rod or a piece of wire is homogeneous, when we say homogeneous, what do we mean? It's like the same material throughout, right? Then its linear density is uniformed and defined as the mass per unit length. That's the Greek letter rho is equal to mass over length, and measured in kilograms per meter. Suppose, however, that the rod is not homogeneous, but that its mass is measured from its left end to a point x is f of x, as shown in figure 5.
It's not easy to actually kind of.
The mass of the part of the rod that lies between x1 and x2 is given by delta m, which equals f of x2 minus f of x1. Stop talking. So the average density of that part of the rod is just going to be the slope, right? Change in mass divided by change in length. Right? That's going to be our average density. Density is mass over length, or mass divided by length in this problem. Now, if we let delta x go to 0, that is, if we let x2 approach x1, we are computing that average density over smaller and smaller intervals. The linear density at x1 is the limit as that delta x approaches 0. Which will be the derivative of m with respect to x, right? That's just our definition of a derivative. It's okay. Thus, the linear density of the rod is the derivative with mass with respect to length, okay? For instance, if f of x is equal to the square root of x, where x is measured in meters and m in kilograms, then the average density of the rod, of the part of rod given by x is less, or 1 is less than or equal to x is less than or equal to 1.2 is
Maybe.
So we have m is equal to square root x, right? If we do the derivative with respect to x of both sides, what do we get? I get dm dx equals 1/2 x to the negative 1/2, right? Everybody agree? If we evaluate that at 1, there's meters, right? So that's like our instantaneous.
Like how is 3 times the square root different? Don't just pretend that didn't happen.
I will. Compare that to our average change, which would be let's do this.
Oh.
So I get about 0.48. So this is our average linear density. And this was like our instantaneous linear density. What do you think? Pretty close? Yeah, 0.5 is pretty darn close to 0.48. Is that surprising? Probably not, right?
It's surprising that was like, there were so many words for.
Context matters, right? Like you need to have units, you need to understand what it is you're doing. Now the actual calculus is pretty easy.
They should give us like the whole story and then stuff we actually.
Yeah, that's what it says on my schedule.
It's so funny.
That doesn't make,
Could
that
have just
doesn't
had a
make.
5-minute class.
I don't know.
But like, but,
Shh.
doesn't make any sense.
Okay.
What? Or gave us a
Actually, I'm going to skip and we're going to do this one because I know that people have asked business questions a million times. So let's do an economics question. Right? So it says here, suppose C of X is the total cost that a company incurs in producing X units of a certain commodity. The function C is called a cost function. If the number of items produced is increased from X1 to X2, the additional cost, the change in cost, delta C, which is equal to C of X2 minus C of X1. And the average rate of change of that cost is delta C over delta X, yada, yada, yada. The limit as this quantity as delta X approaches 0 is the instantaneous rate of change of cost with respect to the number of items produced, which we call the marginal cost by economics, or by economists, excuse me. Since X often takes on only integer values, it may not make literal sense to let delta X approach 0, but we can always replace C of X by a smooth approximating function as in example 6. I'll explain what that means if we really need to. It doesn't really matter though. Not to you guys. I mean, it matters, but yeah, not for us. Taking delta X to equal 1 and n to be large, that is so that delta X is small and compared to n. The derivative of C of n is approximately C of n plus 1 minus C of n. Why? We're basically just plugged 1 in for delta X, right? That's all we did. That's all that's coming from, is that the average marginal cost will approximate the instantaneous marginal cost if n is big enough.
The average marginal cost will equal the instantaneous marginal cost if n is big enough.
Approximate, we want to say, but yes. Okay, that's all we're saying there. Thus, the marginal cost for producing n units is approximately equal to the cost of producing one more unit. It is often appropriate to represent the total cost function by a polynomial, where A represents the overhead costs and the other items the other terms represent the cost of raw materials, labor, and so on. For instance, suppose a company has the estimated cost in dollars of producing X items is, then the marginal cost is this. The marginal cost at the production level of 500 items is da-da-da-da-da, which gives the rate of at which costs are increasing with respect to the production level when X equals 500, and predicts the cost of the 501st item. The actual cost of producing the 501st item is close. Economists also study marginal demand, marginal revenue, marginal profit, which are the derivatives of demand, revenue, and profit functions. These will be considered in Chapter 4 if we develop techniques for finding maxes and mins. What I would like for you guys to do I don't know. Some people write it down, Sergio.
No. I'm saying how you say 1 through 3 odd and not just 1 and 3.
No. Well, yeah, fair enough.
I mean, do you?
Captain Critical, we'll do it your way.
Who still has not?
But
Who's so
6,
mad?
but 6 I want you to do.
Oh, yeah.
Then you do 1 through 5 odd, and then 6 and 7.
The circle.
Could do that.
On the test was the double derivative, like, or second derivative question.